Good afternoon. We're this close to reading break. Eek. Think of all the things you're going to get done. It's going to be amazing. It's going to feel so good. Maybe. Okay. So I've been working away on some stuff, and well, you probably noticed that your labs are marked finally. I don't know. I just kept forgetting about them. So my apologies. They're finally marked. I think you have to scroll down to the very bottom to see if there's any feedback, but also how you're graded. So if you have any questions about that, then just send me an email. It's probably the easiest thing, because my inbox is my to-do list. So, okay. Right now they're hidden because I didn't want anyone to try it yet. Okay, but I have been putting together some electronic things that we can work on instead, because that gives you a grade quicker, obviously, and immediate feedback. And one of those is called an assignment, and another one is a lab. Now you'll notice that they are hidden right now, and there's a reason for that. The assignment is ready, so I'm going to show it, but don't try it yet because I need to do a run through and make sure that it's working. So don't try these yet. Okay, I'll send out an announcement when you're, or maybe I'll put a little note underneath it that it's ready to go. Okay, so I am going to hide it right away, but I just wanted to show you what to expect. Okay, and so the first assignment, so what I'm trying to do is I'm trying to make assignments, and of course chapter 1 was a while ago, so it's just 11 marks, and you can start it, and what you'll have is I'm just seeing if it tells me the penalty. Okay, so you'll notice that a lot of these are multiple choice. Okay, and so unlike Stat 230, where you were able to try it as many times as you wanted, I'm expecting a little bit more from you now. And so you only get 4 attempts, and only 2 of those are not penalized. Okay, after your second attempt, you're penalized by 25%. Okay, and so I'm going to go back here and hide it because it's not quite ready for you. Okay, you'll have all of reading break to work on it, and I can extend it, but it's not quite ready. I want to make sure that it's nice and good, but you'll see it's just going to be quite short. So I'm programming these, and it's a new language. So right now I'm learning 3 new languages. Well, we're using GitHub, so it's not really the language Git, it's just how to use GitHub, but I'm learning that with you. I've used it, but not, I don't think, properly. I don't think. But usually what happens when I think that is, it turns out that I was. And there's nothing more to it. But anyways, I have used it in the past, but it's been a long time. So I'm relearning GitHub and Python with you guys, and how to program in MyOpenMath, which, because none of these questions exist. So I'm busy. But I am putting together assignments for each chapter. Okay. And they will have 4 attempts, but penalized 25% after the second attempt. So after the second attempt. Just to clarify, that's attempts 3 and 4. Right, so attempt number 3 would penalize you 25%, and then chapter 4, or sorry, the fourth attempt, sorry, I'm reading something else. The fourth attempt would be another 25%, right? So that's bad. So you want to make sure that you get these, right? You do have late passes. I'm pretty sure I gave you something crazy like 10 late passes. So if you haven't used this this platform before, I mean, nothing changes for you, but now you have these fun things called late passes, and you should have, you each have 10 late passes that must be applied before the due date. Yeah, so I'll talk about the lab assignment in just a second. So you each have 10 late passes in total, right? That must be applied before the due date. To extend the deadline by 24 hours. There's no limit to how many late passes you apply to an assignment or a lab, but the late passes go for both. Okay, and so if you need more time, then make sure that you apply that deadline or that late pass. Man, I can't talk at all today. I need a break. Right, so just like when you're working with a client, you don't wait until the due date has passed to ask for an extension, right? People aren't upset when you ask for an extension. It's when you ask for an extension after the fact that doesn't make sense, right? And so same idea here, right? You have these late passes, and if you feel like you need them, then you have to apply them before the deadline. Okay. So it's going to be, so the assignment for chapter 1 is kind of brief because that's already happened. And it's going to be theory. So I'm trying to separate the theory from the applied portion. And so the next thing I want to show you is I've made a lab. Now it's incomplete, so I'm not even going to unhide it, but I do want to show it to you. Let's see here. Okay. So you can see it's incomplete right now, and I'm going to take a screenshot here and save so I can write on it. I am also putting together some more lab exercises. Right, and it's in the works right now. Let's just cut it to here. Okay. But I am so proud of myself because I was able to program it to generate a data set that's going to be random for all of you. And then, so what you're going to do is you're going to download that CSV, and then you're going to bring it into RStudio, and then you're going to do these calculations, and you can choose whether you want to use R or Python. I don't care. In fact, I would never know if you were using Excel, for example, but the exercises are meant to help you figure out how to do it in R or Excel. So all I'm going to do is I'm going to, and I made up this data set. It's a silly data set, but consider this entirely fictional. So that means fake data set, which randomly selected some number of students across the country and asked how many donuts they eat per year approximately. these are just randomly generated numbers, but that doesn't matter, right? So download the data. So you click this download CSV, and then you'll have the donut data and import into RStudio. So you should know how to do that. If you don't, then the textbook shows you. So you're allowed to use R or Python. I honestly don't care, right? It's just trying to get you to do it. If you're using R, one of the things that I asked you to think about was trying to get the decimal places to match, right? And so usually you have to make sure that it shows enough decimal places, right? So you might have to figure out how to do that. I would say 15 should be safe. 15 should be safe. Usually I do 15, just why not? If I'm adjusting the number of decimal places it's showing, why would I limit it to 4 or 5 or 6, right? I'm just going to go for 15. Okay. And then give all your answers to at least 4 decimal places if you have to round, right? If it's a whole number, then you can just put in the whole number, and that's always true. Okay. And so what I'm building is you have to find the mean number of donuts, and hopefully this feels very, very easy, right? Find the mean number of donuts, find the median number of donuts, and then so on and so forth. And more questions under construction. Okay. So that's what I'm working on, and you can expect to see those over reading break, but I'll give you lots of time, and I can give you time after reading break too to work on them. Okay, and they're really just for your practice, right? But that's true for anything, right? That's true for assignments, it's true for labs, it's just for you to practice and prepare you for the test. Okay, so good. So just be aware that those are coming up. And so far, right, I only have 2 things. I was trying to make sure that it was running and working, and then I ran out of time. I had to go to class. Anyways, isn't that life? Okay. Exactly. Yeah, so much to do. Hey, is that a cute toolbox and a screwdriver? Yeah, I know reading break is not a break. It's like time to yeah, you might need it. Yeah. Yeah, reading break is never a break, even though we head into it thinking it's a break. It's like time. All right, so all right, let's see here. So you'll have lots of time to work on those. Okay, and I want to do, I think I mentioned last day, but we'll do test number 1 after chapter 3, right? And so it would be a good idea to read chapter 3 before we get back after reading break. So it would be a good idea. It would be a good idea to read chapter 3 over reading break. Okay. And then we'll do test number 1 after chapter 3. And like I said, I have stuff that I need to work on too over reading break. You're not the only ones. Oh, no, no, no. Right. I want to do nothing, but that's not going to happen. And so I have to kind of figure out, I have a pace that I want to be going at, but we're kind of slipping behind. So test number 1 will cover up to and including chapter 3. Chapter 3 is mostly review, so that's nice, right? So a lot of stuff is going to be familiar, and then we're kind of filling in the gaps with some stuff that might not be familiar. Okay, so most of it's familiar though. Okay. So we were talking about different distributions. We weren't really talking about how to use them, right? It's just when do they apply? Yeah. So let's see here. Because I think we just wrapped up the binomial distribution, so I'm going to leave it at that and just pick up fresh. Okay, so we were discussing different distributions and when they apply. Okay, so let's see here. The next distribution, which we have seen, we saw in Stat 230, is the chi-squared. So we read that as chi-squared. Square or squared, it doesn't really matter, distribution. So we talked about the normal distribution. We talked about the t distribution, the student's t distribution. We talked about long-tail distributions. We talked about the binomial distribution. And so now we're going to talk about the chi-squared distribution, but really only touching on ideas. Okay, and so the chi-squared distribution is, you might remember the formula, right? It had something to do with observed minus expected, and that's exactly what it's measuring. Okay, it's measuring the departure from expectation in counts specifically. Okay, and so it's used the chi-squared distribution, and I'm not drawing chi very nicely here. I think it has kind of this like that, a little bit more flourish, but I just write it like this. The chi-squared distribution is used to model departure from expectation in counts. Departure from expectation in counts. Counts are from categorical data, right? And so here, right, this means that we have, therefore, it's for categorical data. So whenever we have categorical data, one of the things that we can consider is the chi-squared distribution, right? Or what's another thing I can consider? I have the binomial, right? The binomial models the probability of some number of successes, right, in some number of trials. So that's a little bit different from, okay, if I have this distribution of counts, so now I'm talking about the chi-squared distribution. If I have this distribution of counts, how does that compare to what I would expect if things hadn't changed, for example, right? Or if it was the same as some other group. And what we saw was there are many different ways that we could calculate this chi-squared for different scenarios, but the idea always is the same. It's always the departure from expectation. In fact, the formula, we're not going to use it, but it's nice to see the formula and link it back to, okay, the departure from expectation, meaning what? So the chi-squared statistic is the sum, and there are kind of ways we can simplify this, but one of the ways is the observed minus the expected value over the square root of the expected value squared and then summed. Okay. And so departure from expectation, that's this, right? The observed minus the expected. Sorry, O is observed and E is expected. Observed count versus the expected count. And usually it's the count in some cells. Yeah. Okay, so that's where the departure from the expectation. So I have some observed count, and then I subtract what I was expecting to see, and then I take into account the square root of the expectation, or, you know, we can rejig this a little bit, but not much. They always end up being the same anyways. And so the square root of the expectation just takes into account, okay, well, how far from the expectation are we? And then if we square it, then we're making all these values positive and then add them all up, right? Then we're able to add them up and get a good measure. And that is our chi-squared, okay? And so what does that mean? What is our value of chi-squared if the observed values are close to the expected values, right? Then the observed minus the expected is going to be small. Right? And then even if I take into account what the expectation is and I square it and I add up, then chi-squared would also be small, right? Because it's in the numerator. So here, if the observed counts are close to the expected values, or are close to the expected counts, O minus E would be small, right? Then chi-squared, which is the sum of O minus E over the square root of E and then squared, right? Then this would be small, which means that a small number divided by, so the expected is not really the predicted, although you can think of it as the predicted, but it's technically not the predicted. The expected count, so for example, if I have 4 categories, let's see here. So for example, consider grades. You can have an A, B, or a C, or let's just cut it at F. Okay. So then I can have my observed count, which maybe is 6 and 12 and 3 and, well, maybe more likely 9 and 3. Let's do that. Okay. That makes a total of how many? 6 plus 12 plus 9 plus 3. And of course, we wouldn't do this, hey, it magically added up to 30. It was an accident, but a happy accident. Okay, so what was I going to say? Oh yeah, we're not doing these by hand anymore. We did these by hand in Stat 230. So we are going to leverage software to do it, but we can be quite dangerous if we don't know what it's doing, at least a little bit. So I disagree with, you have to know all this theory behind what's going on. I don't feel that way, although I was raised that way, or raised that way, right? But I disagree. But we do have to have some idea of when things are appropriate, right? So it definitely helps. So if I wanted to test, right, if the distribution of counts is equal, right? So now I would expect an equal distribution across these categories, right? So consider grades. Are they equally distributed? Okay. So if they are equally distributed, then what would happen? I would expect, well, if all of these grades are equally distributed, then I would expect this 30 to be equally distributed across the 4 categories, right? So then I would have 30 divided by 4, which is 7.5. And maybe I should, no, it's okay. It's okay. You're allowed to have decimal expectations. Okay, so 30 divided by 4 is 7.5, which means I'm expecting 7.5, 7.5, 7.5. If they were equally distributed. If they are equally distributed. Across the counts. Okay. And that's not always the case. We're not always looking for equal distributions. We might have some distribution in mind that I want to check against. And so that's where the chi-squared comes in, right? And so now I have this observed count, 6, minus the expected. So I take the departure from the expected value, which is 1.5, right? Or negative 1.5. Okay. Awesome. And then I can divide it by the square root of the expected value, and then I square it to make it positive, and then I can add these up. So let's go back to here. So if the observed counts are close to the expected counts, then this observed minus the expectation is small. And if you take a small number and you divide it by a value, that's still going to be small, right? And so then this is small, which means when you square it, it's still going to be small, right? And so overall, chi-squared is small if the observed counts are close to the expected counts. Okay. So overall, if you have a small deviation, then you get a small chi-squared. And of course, we've seen the chi-squared table, which gives us some probabilities, right? But we can use software and it'll just find the p-values and the probabilities for us, right? And so the chi-squared is small if it's close, right? And if the, maybe I'll do this. If the, let me see here. If the observed counts are far from the expected counts, chi-squared will be large. Okay. It depends on the number of categories, right? But how did I draw? Yeah. Chi-squared is the observed minus the expected over the square root of the expected squared, and then add them all up. So if this is large, how can I? Then of course, this is also large. And then the squared values and the sum is also large, right? Same idea. So it all hinges on what the observed minus the expected is, which is the deviation from expectation. Okay, so chi-squared is considered a goodness of fit test. Okay, and there are many ways that we can use chi-squared, or there are some common ways that we can use chi-squared, but the most common is this goodness of fit. How well does our observed distribution of counts, how well does that match the expected distribution of counts, right? That's the goodness of fit in this case. So chi-squared can be used in a few ways, right? As a test statistic, and we saw two, goodness of fit and independence, right? Are these two groups independent of each other, right? Or two categorical variables independent of each other? And so chi-squared can be used in a few ways, but the idea stays the same, right? How far are the observed counts from the expected counts? But most often it is a goodness of fit test. We've seen the t distribution, right? The shape of the t distribution depends on the degrees of freedom. It depends on the sample size. Okay, and so recall the shape of the t distribution depends on the degrees of freedom. Oops, from freedom, which is often just the sample size minus 1 or some variation of that, right? And so degrees of freedom is n minus 1. So it depends on the sample size. Which depends on the sample size. Okay. So in a similar way, the chi-squared distribution also depends on degrees of freedom. Okay, but those degrees of freedom now are going to be from often the number of categories, right? And so if we think back to Stat 230, we've seen 3 different t distributions, or at least the core ones, right? One sample mean, matched pairs, or 2 independent sample means. And for one independent sample, one sample mean, we have n minus 1. For matched pairs, we have the number of differences minus 1. And for 2 independent samples, we take the smallest of the sample sizes minus 1. So either way, it's a sample size minus 1. Okay, so now, even though the idea is different depending on the scenario and the tests that we have, right, the degrees of freedom for chi-squared is going to depend on the number of categories, right? In the same way that the degrees of freedom for the t depends on sample size. So chi-squared also relies on degrees of freedom. Which will depend on the number of categories. Which will depend on the number of categories. And there are different ways, right? If we just have one categorical variable, then it's the number of categories minus 1. But if we have a 2x2 table, then we take the number of columns minus 1 times the number of rows minus 1. So it totally depends, but either way, we have the number of categories, right? Okay, good. So chi-squared is for categorical data. Okay. So now the next distribution I want to introduce is the F distribution. Okay. So the F distribution is pretty much the same. So notice how we're not doing any examples using these. We're just introducing the distributions, and then we're going to go back and we're going to refer back to these, right? And so what we're really solidifying here, or trying to solidify, is when would we use each of these distributions? When should I be using this distribution? And that takes a lot of practice, right? And a lot of time. So when do we use the F distribution? The F distribution, again, just like the T or the chi-squared, we can apply it to many different scenarios. But in general, it's if we are comparing numerical values across groups. Okay, so now we've got a mashup of numerical data and categorical data. And so the F distribution compares measured continuous values, and I'll put in brackets here, numerical data, right? Numerical data across groups. And so across groups, which come from categorical data. Okay. So notice that the only real difference here is instead of counts, right? I'm looking at these measured values, this numerical value across groups instead of counts. So here, versus the chi-squared, which compares counts across groups. Okay. So the chi-squared can be used for even just one categorical variable, although it's kind of boring. Usually we do two. Okay, so that's the difference between the two, but the idea is similar. Okay, and the F distribution can be applied to a couple of different scenarios, and it's very common. And in either scenario, it's going to be called an ANOVA, which we've seen one of, right? One of in some detail, right? And then now in this course, we'll see a couple more, but it'll just be part of our output, right? So the important thing for us is to have an understanding of, okay, when can I use it? And what does it mean, right? So F, if we think about it this way, F is going to be a measurement, and it compares the variability among group means, or maybe among the groups, maybe I'll say that, among the groups divided by the variability within each group. Within each group. Okay. And so this is why we call it an ANOVA, an analysis of variance, right? And so what it does, and the reason I'm being kind of vague, or really vague actually, is because sometimes we use it to compare group means, right? For more than 2 groups, then the natural progression would be to use an F statistic to compare means, right? So let me see here. We can use F to compare more than 2 group means. But we can also use it to compare coefficients in regression output. So, I'm not going to write that out because it's going to come up, but it's basically looking at, okay, numerical data in each of these groups, and then it's looking at the variability among the groups. So among the groups means, okay, if I go from one group to another, how much variation am I expecting there? And then what it considers is, okay, well, how much variability do I have within each group, right? And if the variability among the groups is huge, but then if the variability within each group is not that much, right, then those would be considered different, right? And so then we would get this F statistic that is high, right? And so if there's no significant difference, right, then we get to see an F that's close to 1, right? And so an F close to 1, right, means, and I shouldn't use the word means, an F close to 1 shows there is no significant difference between the groups. And just like the others, we're going to have degrees of freedom again. And we're going to talk a little bit more about degrees of freedom. So far, I've kind of said, okay, well, just take it for what it is, right? We're going to talk a little bit more about it and kind of talk more about the idea of them in chapter 3. But for now, let's just know that most things that we're going to deal with require degrees of freedom. So it's our job to know how you find them. And so F also relies on degrees of freedom, and it's usually related to the number of groups, okay? But it's a little bit different. So F, because this is the last thing I want to say about the F distribution, so I'm going to keep it on this page. F also relies on degrees of freedom, and usually the number of groups. Maybe I shouldn't have that tilde there. Maybe I should put it in front. So it's related to the number of groups. Yeah, so you can use the ANOVA or an F statistic to compare group means, but you can also do it to compare different coefficients in a regression. So that's why I'm being vague. It's on purpose. usually it's to compare group means, but then we can compare betas too. And I'm sure there's other things that we could compare using F, but those are the only ones that I know so far. Good. So could you use it between for two samples? In theory, yes. But then we have the two independent samples t-test instead. And so I would probably use the T for as long as possible, and then I would switch to F when I had to. But I think in theory, unless you run out of degrees of freedom, I don't know. I think in theory you can do it, but it should be the same or very, very similar to a two sample t-test. But good question. I guess I totally avoided it by saying this here more than two. Cheeky. Okay, so so the chi-squared, the F statistic or the F distribution. What's another distribution that we might use? Well, you don't know them yet, but one that we've seen briefly, ever so briefly, was the Poisson, right? So the Poisson distribution, and it's on a first page, so it's going to look weird for a bit here, but it's okay. The Poisson distribution. Now, our job is to remember when we can use it. Okay. Poisson, first thing I want you to think is counts. Okay, and so the Poisson distribution is the frequency distribution, and I have to copy it out because it's very similar to another one. So is the frequency distribution of the number of events in sampled units of time or space. So the Poisson is sort of weighted, sort of. So we're gonna have, yeah, so it's weighted in the sense that we have some lambda, some parameter that tells us how often things happen. But then, so in that sense, yeah, I would say yeah. So the Poisson distribution is the frequency distribution of the number of events in samples or in units of time. Take it back, in sampled units of time. Units of time or space. Okay, so this is the one that we haven't spent that much time on, right? And there's going to be a couple more that we didn't even introduce in 230. Okay, and so the Poisson is one of those that we kind of breeze through. Okay, but if you have some rate of, okay, customers come to my, oh, I don't know, I must have clicked something there. Customers come to my website at this rate, okay? Then I can figure out, okay, the number of people that are gonna come to my website in a 3-day period, right? So, so that would be in units of time or space. So especially if we're looking at defects. So if you're ordering a countertop, or especially if you're producing a countertop, for example, like a physical thing, then the number of defects could be counted using the Poisson distribution if there is some rate that these defects happen at. Okay, so it can be in time or in space. Okay, and so it requires, the Poisson requires an estimate of the average number of events per unit of time or space, right? And so that's the first thing that you need to know, right? So if I'm your client and I ask you, okay, how many people are going to come to my website on this day, then what would your first question be? Well, on a typical one of those days, how many people do you see? How many people do you see per hour, right? And then I can figure out how many to expect, especially if there's going to be an increase, right? So for example, the Super Bowl was just on, right? And so a lot more people are going to be watching TV. I didn't, but I never do. So nothing new there, right? But people who don't usually watch TV at that time are still watching TV. And so they need to be prepared for that, right? And even if you are advertising in the Super Bowl, will it pay off, right? And so you need to know how many people you expect to be reaching with your ad, right? So the Poisson comes up in many different scenarios. So the Poisson requires an estimate of the average number of events per unit of time or space, right? Depending on the question. And this is what we call, so the rate is lambda, right? The Greek letter lambda. Okay. It's a B there, lambda. Okay, and so the rate is that estimate of how many people per minute are going to be watching, how many people per hour are going to be watching, right? And then depending on the number of units that you're interested in, you'd have to take that into consideration, right? But so lambda becomes the mean number of events in that specified time frame. So that's not weird, right? The crazy thing is, for a Poisson, the variance is also lambda. So the variance and the mean are the same in a Poisson distribution. And that's kind of like wild and wacky, but we just take it as fact, okay? We're not going to dissect it or do anything with that. It's just a fact. Okay, and so lambda is the mean number of events in a specified interval of time. Specified interval of time or space, of course. Yeah. So lambda is the mean, but also lambda is the variance of the number of events in a specified interval of time or space. Variance of a Poisson. Now, how can there's a particular, I want this one. It's very important. I'm going to take that time. Hey, there. That's crazy, right? Oh, didn't increase my emoji. Anyways, doesn't matter. There, zoom in instead. right? So it's the mean and the variance, and that's crazy. Okay. We looked at briefly how to calculate these things, and the code libraries that you're building are of course going to show you how to generate random data from a Poisson, and then we can look at that, right? Or we can test a Poisson and we'll be able to deal with that. So our job is mostly going to be identifying a Poisson distribution, right? When is it a Poisson situation? Okay, it's a little bit tricky because the next few distributions are kind of similar, right? And so that's what makes them hard to keep track of, right? So the next distribution is the exponential distribution. So if you're counting things in either time or space, right, and you know the rate that they happen at, then you have a Poisson. Okay, whereas the exponential distribution the exponential distribution is going to be the distribution or the frequency distribution of the time between events. Yeah. So if I make a sale, how long will it take approximately to make another sale, for example, right? And how long, so now notice all these scenarios have to do with how long between these events, which means that I, again, need to know the rate of those events, right? And so that lambda is going to come up again, but now I'm talking about the time between events. So the exponential distribution, oh, I should capitalize it for now. So the exponential distribution is the frequency distribution of the time or distance. Remember, we talked about time or space, right? So typically we're talking about time, but if we're talking about space, then how much of this countertop, and that's kind of the most obvious thing with defects that I can think of producing, or maybe you're producing fabric, right? How long is it safe until I'm going to have to cut it because there's a defect, right? How much am I expecting to keep? Okay, so the exponential distribution is the frequency distribution of the time or the distance from one event to the next event. Okay. The exponential distribution also uses lambda. And one thing that I do want to point out is that the exponential distribution can be used to model time to failure, but we're going to have a more reasonable time to failure model or distribution, which is the Weibull distribution. Okay, and so you can use the exponential distribution to model time to failure, right? The exponential distribution is the frequency distribution of the time or distance from one event, so the start time, to the next event, which would be when the thing fails, right? Time to failure. And so, for example, we understand that this calculator is going to fail one day. There's something's going to happen and it's going to stop working, right? And so we could use the exponential distribution to model that. However, that would be assuming that the rate of failure or the rate of this event happening stays the same over time, which is not really true, right? In the beginning, it would be very, very unlikely that it would fail, right? And then the probability of it failing is going to be increasing over time. So it's not fixed anymore, right? As it was for the Poisson and now for the exponential. So then we introduce the Weibull, which we'll finish off with. But that's the difference between the two, okay? So the exponential can be used to model time to failure, but only if the rate, right? And so the rate, which is the same as this rate, right? The rate of events, okay? The average number of events per unit of time or space, that's the same lambda that we use here. So the exponential can be used to model time to failure if lambda is constant. Okay. Usually not the case. So the exponential distribution also uses lambda. Okay. Which is the rate from the Poisson distribution. And it assumes that that lambda is constant. Okay. So here, but it assumes lambda is constant, which is not always the case. Not always true. Okay. So, for example, if you think about a printer, right? A printer can print some number of pages, but there's going to be some, ink blot or whatever at some rate, right? And so that rate is not necessarily the same over the lifetime of that printer, for example, right? And so so here the exponential distribution assumes that it's the same. So it works the same, and then it dies, and that's it, right? And then it's over, right? One thing that we can do to work around this, if we want to use an exponential distribution, or if we think that the exponential is still usable, then we can break up this interval into kind of reasonable chunks, and then we can have constant lambdas within each interval, right? And then that lambda could change. It might be reasonable. It might be reasonable to break up a larger interval into smaller intervals, each with constant lambdas, right? So it might be reasonable to break up a large interval with non-constant lambda into smaller intervals each with constant lambda, right? Different constant lambdas. Okay. So that's one of the options that we have. So how do we find this lambda, right? And so this lambda, we can think of it, we can call it the failure rate if we want, especially if we're considering time to failure. Usually we're counting defects or something going wrong, right? And so usually we'll have a pretty good idea of lambda from previous data, right? So from previous years, we have this understanding, and then we just have a good guess of what lambda is, okay? That's not always the case though. And so if we want to estimate, we're estimating the failure rate, it's not a distribution, but I'll underline it anyways because it's one of the subsections. But in many applications, right, especially if you think about advertising, for example, advertisers have a good idea about how many people see and purchase things from their ads during the Super Bowl, for example. And then they use that to say, okay, well, if I spend this much on an ad, is it going to be worthwhile? That kind of thing. And so in many applications, we can approximate, and the keyword there is approximate because we don't actually know it, but we can approximate lambda from prior data. Okay. What about rare events? What about if we definitely would want to model things like when is an airplane engine gonna fail? Okay, I don't really want to have a lot of data on that. I want to replace the engine before it fails, right? But in order to know when it's going to fail or anticipate when it's going to fail, I need to know the failure rate. Okay, and so yeah, we could probably scrunch up some information, but hopefully airplane engines are being replaced before they fail, right? And so then we don't have any data, ideally. So we either have very, very little data, right? Or we have none at all. So then what we do is we simulate different lambdas, and then we try to match it to the little data that we have. So let's assume that we have a little bit of data, right? And then we try to match it, and the one that matches the best, that's the lambda that we're going to go with. So we generate all these different lambdas, and then we look at how they would all behave, and then the one that behaves most closely to the little bit of data that we have, that's what we're going to go with, right? And we might make adjustments just to be safe, right? But that's the idea. When considering rare events with very little data, hopefully, we can make guesses and simulate them, right? And so we generate all these different scenarios, right? And then we match them to what we actually saw. And so when considering rare events with very little data, we can make guesses. We can make guesses and simulate outcomes to estimate threshold values, right? We don't want to push it to the max usually, right? But we do want to have some sort of threshold values, right? So lambda will be larger than this value, right? Or smaller than this value. And so let's see here. To estimate threshold values for lambda. Okay. So the last distribution that I want to throw on you guys is the y-bowl distribution. Okay, and there are many other distributions, right? And so there's the gamma, the beta, there's all kinds of distributions, okay? But we're just going to focus on these. Okay, so don't be discouraged if if you're having different distributions thrown at you. That happens. There's a lot out there. Okay, but these are the ones that we're going to focus on. Okay, and so finally, the y-bowl distribution is that generalized version of the exponential distribution that we talked about, right? Where the rate, the lambda, is allowed to change, right, over time or space, right, depending on what we're talking about. And so the y-bowl distribution, I guess I should write it out, is a generalized version of the exponential distribution, where the event rate, so where lambda, so where the event rate lambda, put in brackets, is allowed to shift over time or space, I guess, is allowed to shift over time. Usually we focus on time, but I'll fill it in with or space, but usually it's time. I guess I shouldn't put a period there. I should put it there. Okay, but usually it's time. Okay, and so usually we're using this for time to failure models, right? And so right, for example, mechanical failure, or just in general, time to failure analysis, right? Or in general, time to failure analysis. Yeah. That means that we have a couple of things that we need to incorporate, right? We have what we call the beta, which is going to indicate if the probability of something happening is increasing over time or if it's decreasing over time, right? One example that I would think about is if I post something for sale on Marketplace, right? If I don't sell it right away or within a week, then it's less likely that I'm going to sell it, right? And so as time goes on, the probability is decreasing as time goes on, right? That's kind of a poor example because I guess the sale would be the defect. I don't know, but that's the one thing that comes to mind, right? You can think of different scenarios, but the y-bowl has a shape parameter, beta, which you probably should know is the Greek letter beta, right? Beta. Okay, and if beta is greater than 1, then the probability of something happening is increasing over time. probability increases over time. Whereas if beta is less than 1, then the probability decreases over time. Okay, so it depends what the scenario is, but it has this shape parameter for that reason. Okay. And so for time to failure analysis, which is when we use the Weibull mostly, right, we don't use the rate anymore because it's only going to fail once, hopefully. If it fails, it doesn't have the chance to fail again, right? So a machine can only fail once. And so we don't really have a rate anymore. We have what we call a scale parameter. Okay, and so for time to failure, models, we do not use lambda. Oops, it looks like one word. We do not use lambda. We use eta. We use this kind of fancy n, which is eta. Okay. Which denotes characteristic life, right? So batteries, for example, a battery is going to fail at some point, right? Once it's exhausted. But I know some of our batteries don't work that well in the cold, right? And so then all of a sudden you're starting with this less characteristic life than you would have in the summertime when things are nice and warm, right? And so so we use eta. We use eta as the characteristic life. Which is a scale parameter. Okay. And I see that I'm all out of time, and my apologies, but that was the last thing I wanted to say. I wasn't checking. I hope that you have a really, really great break and you get everything done that you want to get done, and maybe then some. But if you have any questions, let me know. So many assignments. If you have any questions, let me know. Otherwise, I'll see you after the break. Stop this here.